Welcome to this mini course in Elastohydrodynamic Lubrication. My name is Roland Larsson. I'm a professor of machine elements at Luleå University of Technology in Sweden. And I will discuss in this 4-part lecture about different things in this field of elastohydrodynamic lubrication. So what is that? We will discuss exactly that issue. What is EHL? What are the mechanisms of EHL? Why does it work? And you will also, in the end of this lecture, learn what this picture shows. EHL, what is that? That's the first question. In the upper right corner here you can see a rolling element bearing, and elastohydrodynamic lubrication, that's typically the type of lubrication found in bearings of this type. And in a bearing like this, the contact of the two surfaces are what we call non-conformal. And non-conformal surfaces means that the actual contact region is very small. The contact force is transmitted over a very small area. And that implies that the contact pressures become very high. In a bearing like this, typically the pressures can be gigapascal range. Could be up to even 4 gigapascals maybe. And at that pressure, the surfaces are really deformed. They are deformed elastically. They mustn't be deformed plastically, because then they are damaged. But they are definitely deformed elastically, and that is good. Still, a lubricant film is formed in between the surfaces, and even if this film is very thin, can be in the order of micrometer or less than 1 micrometer, maybe only a few nanometer thick in many cases. Still, it's there, and it's very important that it's there to protect the surfaces. And as I said, the rolling element bearing is a typical example, but you can also find this lubrication type in gears, cam mechanisms, and many other applications. If you compare a rolling element bearing with a journal bearing, you may find that it's a little bit maybe unexpected that this non-conformal contact in the ball bearing here can actually carry as much load as in the conformal bearing, in the journal bearing here. If you typically, I would say, if you see in a bearing catalog, you may find that a bearing with inner diameter of 50 millimeter may carry a load something like 6 to 87 kilonewtons. If you apply that load to a journal bearing with the same journal diameter, you will get a projected pressure of 5 to 70 megapascals. That's pretty much to be a journal bearing. And so I would say that the bearings, these two types of bearings, can carry about the same load. Sometimes the ball bearing can carry even more. How can that be possible? That's what we are going to learn in this mini course, I would say. There are different types of EHL. The type of EHL we will discuss mostly in this course is the hard EHL, which you can find in machine components. But you should also remember that there is something called soft EHL, still in non-conformal contacts, like in lip seals, in bearings, and in the contact between the tire and the road, a wet road. That's still EHL, but the surfaces are so soft that the pressure range is only in megapascal range. It never reaches the gigapascal. We can also find EHL in conformal contacts. Here is from the hydraulic motor. In the contact between a ski and snow, you may say that elastohydrodynamic lubrication occurs, and in a hip joint, in the contact between the ball and the cup here, that's definitely a type of conformal EHL. But we will focus on this type, the non-conformal hard EHL. Let's think about a cylinder in contact with a surface, a flat surface. If we apply a load, in this case 2 kilonewtons per meter, just think about 2 kilonewtons per meter, that's the same as applying 100 kilogram over a 1 meter long cylinder. If we apply that load, and we increase the load, and we increase it again, you can see that what is happening is that the contact zone is growing. And that is very good in this case, because that is one of the reasons why it's possible to lubricate a contact of this type. This figure shows how the contact zone grows from the 2 kilonewton per meter case to the 200 kilonewton per meter case. And you can also see how the pressure increases. So the pressure doesn't grow linearly with load. It grows in this case only with a square root with load, and the same for the width of the contact. And that's important to have in mind when we think about the lubricated contact. The important thing here is to remember that a flat region or a contact region is formed, and that this contact region is growing when the load is growing, and that growth of the contact region actually reduces the maximum pressure, it makes it that the pressure doesn't increase very much. So if we start from the dry contact and then suddenly we start moving the surfaces, they start to roll in contact with each other, and you have some lubricant in nearby here. When the surfaces start to move, they are actually bringing some lubricant in between the surfaces, in the gap. They are forced, since the lubricant sticks on the surface, it forces itself in between the surfaces and forms a hydrodynamic lubrication. It's a wedge. You remember from lubrication theory that a wedge must be formed, and here you can see that you have a wedge, a bigger inlet than the outlet, and a pressure is formed, a pressure which is pretty similar to the dry Hertz contact. This is maybe a better picture of this. Again, the solid line here is the new hydrodynamic pressure formed in the lubricated contact, while the dashed line here is the dry Hertz contact pressure. You can see that the curves are following each other almost completely, apart from small deviations here in the outlet of the film. And this lower part shows how the film thickness looks like in the lubricated contact. And this film has some funny features. This is a typical behavior of both the film pressure and the film thickness. From lubrication theory, we remember that the flow that comes into the contact must pass through the center of the contact, and it must also go out here in the outlet, and it must be the same flow as long as the conditions are stationary. Since in the inlet we have the surface is bringing in the lubricant, while the pressure gradient wants to push it back, that causes a flow profile that looks that one plus that one. But in the outlet, you have a Couette profile. The surfaces want to push out the lubricant from the contact, while the pressure gradient also want to do that. So in order to get the same flow in the outlet as in the inlet, you really must have a thinner film in the outlet. And now, since the surfaces are deformed, you can see here the undeformed shape of the surface is a dashed line here. Since the surfaces are deformed, they can actually change their deformation in order to provide this flow balance. And that is what is happening here. So the pressure is actually made in such a case that it closes the gap here. And it wants to close it pretty rapidly like this. And in order to close it pretty rapidly, you must change the pressure. And that's the reason why a pressure spike of this type is formed here. So this typical feature of an EHL pressure distribution must be there in order to provide the good film shape, film profile. So this is an act of the nature law, laws of nature. So you have actually two laws to obey in this case. It's the flow continuity and the force equilibrium, and they work together to in such a way that the film profile is created in this way, and the gap is smaller in the outlet than in the inlet. Another funny thing with this is that the actually smallest film thickness, or the minimum film thickness, occurs almost outside the contact, where the pressure is pretty low. So you may expect that the smallest film thickness should occur in the center of the contact, somewhere here, but it doesn't. It occurs out here in the very end of the contact. Alright, that was a line contact. If you run a test with a point contact, it will look something like this. This is an interferogram where each white or dark or bright circle here corresponds to uniform film thickness. So it's like a contour map. So this, for example, this black line here is corresponding to the same film thickness, and those concentric rings are just showing the spherical shape of the ball. And the ball is moving in this direction, so the oil is coming in here, and you can see that this area is pretty flat. It's almost the same film thickness here, while here, along here, a horseshoe shaped constriction or barrier is formed. So the actual minimum film thickness occurs here and here, again in the outskirt of the Hertz contact, which is around here somewhere. That picture is formed by using something called optical interferometry. We're not going to discuss too much about that, but just to give you an idea about what is happening is that you shine some light on the film. Well, first of all, you place your ball into contact with a flat surface, and this flat surface is transparent. So it's a glass disc with some layer, some coating here, which is semi-reflective. It's a beam splitter. So the light is coming here. Some of the light is reflected in the beam splitter itself. Some is transmitted through it and through the oil film, and then it's reflected in the ball surface instead. And then it's reflected up. And up here we have the microscope and these two light beams, they can interfere with each other. Since this distance is in the order or magnitude as visible light, different colors, different wavelengths of light will interfere with each other and create a colorful picture like this. If you use white light, if you use monochromatic light, you will get something like this. You will get black and white fringes. But in this case, we're using white light, and here, for example, the blue light interferes, and we know the wavelength of blue light, and then we can also determine the thickness here. And again, you can see here the ball is moving in this direction. This is the Hertz zone. The smallest film thickness occurs here and here. So it forms a kind of barrier to stop the lubricant to flow out, to cause an unbalance of flow. This is just another picture of the same thing, but in here we have been using some computer program to compute the film thickness. So from this interferogram we translate it to a film thickness diagram. Now you can see here the flat region here and the barrier here, and on top of this the flat surface is. So this is a 3D picture of the film thickness distribution, and this is the corresponding pressure distribution. This is the inlet and this is the outlet. And you can see here a sign of a pressure spike. Okay. Okay then. So we know that a film is formed because I told you, but it's a tiny contact and the pressures are gigantic. We talk about gigapascals. If you put a fluid there and you press it with gigapascals, why doesn't it just escape? Why isn't it just squeezed out from the contact? Well, the thing is that for an ordinary lubricant or an oil normally, the viscosity increases several orders of magnitude when the pressure increases. This is some kind of schematic diagram showing how the viscosity of an oil increases from maybe 0.02 or something to several orders of magnitude, as I said, millions of pascal seconds at these gigapascal pressures we talk about. And even if it's not a perfect model, but we normally use this relationship to describe the relationship between the viscosity at a certain pressure and the pressure itself. And it's at least at low pressures this is an exponential function, and the alpha constant here is a good material constant to describe the pressure viscosity relationship. And if you measure that for different types of lubricants or different types of fluids, you can see that it's pretty high for some of the mineral oils. It becomes lower for some synthetic oils like the polyalpha olefin and synthetic esters, and for water it's even lower. And it's a pretty big difference between this value for water and this value for synthetic ester. You can see here that this is the increase of viscosity for water. It will hardly reach 1 pascal second, which is still a pretty fluid low viscosity, while alpha 1.6 or even 2, it brings you up here in the very high viscosity range. So actually at these pressures the fluid is not really a fluid anymore. It reaches a glassy state, which is, you may compare to a glass window rather than a fluid. So it's extremely viscous. And now remembering that the film is very, very thin in comparison to its size. If you compare it to a football pitch, then the contact would be 100 meter long, and then the thickness of the film would be something like 1 millimeter to 1 centimeter. So imagine that you put a glass window with a thickness of 1 millimeter over the football pitch, then you place another football pitch on top of that one and try to squeeze out that glass window from the contact. You can imagine that it's pretty difficult to do that. So as a matter of fact, some lubricants trapped there at the center has a very big problem to escape from the contact. You should also remember that the lubricant is overrolled in a ball bearing, for example, over a very short time period, in milliseconds only. So there is no time for the lubricant to escape. So that ends the part 1. Now you know a little bit about why this works and the mechanisms of them. In next part we will discuss how thick will the lubricant film be and can we quantify it. Thank you very much.